Find somewhere comfortable. You don't need to sit up straight or hold anything in your mind. You don't need to follow every word or remember a single thing that's said tonight. Just let yourself arrive here in whatever position feels easiest, and let the words come to you the way distant sound comes through a closed window, present but soft, asking nothing of you. Tonight, we're going to spend some time with one of the quietest and most astonishing ideas in all of science. The idea that nothing, true, absolute, perfect nothing, does not exist anywhere in this universe. That the very space between things, the darkness between stars, the stillness between heartbeats, is not empty at all. It is alive with something. Something patient and ancient and perpetual, flickering away beneath everything, holding the fabric of reality together in ways we are only beginning to understand. If today was hard, if you carried something heavy through the hours and you're only now setting it down, this is a good place to rest. You don't need to bring anything with you into the next hour. The day can stay where it is. We'll move through this slowly, through history, through experiments, through the strange and beautiful physics of the vacuum. And somewhere along the way, if you drift off, that is exactly where you're supposed to go. The words will carry on without you. The universe will carry on without you. It always does, and it always will, and that, when you think about it, is one of the most comforting things imaginable. So, let's begin at the beginning. Let's begin with nothing. For most of human history, the question of whether truly empty space could exist was not a scientific question at all. It was a philosophical one, and for a very long time, one of the most influential minds in the ancient world had settled it to almost everyone's satisfaction. Aristotle, working in Athens in the 4th century before the Common Era, was certain. Nature, he said, abhors a vacuum. He meant this not as a colourful expression, but as a statement of physical law. In his understanding of the world, everything that existed was made of combinations of 4 fundamental substances: earth, water, air, and fire. And these substances were always in motion, always pressing against one another, always filling whatever space was available. A true void, a region containing absolutely nothing, was not merely empty. It was, in his framework, impossible. If you somehow removed everything from a region of space, something would immediately rush in to replace it, because nature would not permit the absence. This idea had remarkable staying power. For nearly 2,000 years, it shaped how educated people thought about space and emptiness. Not because no one questioned it, but because questioning Aristotle required both courage and a very good pump. The pump came first, in a sense, or rather, the tube came first. In 1644, an Italian mathematician and student of Galileo named Evangelista Torricelli performed an experiment that would quietly begin to unravel the ancient consensus. He filled a long glass tube, sealed at one end, entirely with mercury, the heavy silver liquid metal. He then placed his thumb over the open end, inverted the tube, and submerged the open end in a bowl of mercury before removing his thumb. What happened was this. The mercury inside the tube fell, not all the way. It did not empty out into the bowl below. It fell to a height of roughly 76 centimeters above the surface of the mercury in the bowl, and then it stopped. And above the mercury column, at the sealed top of the tube, there was a gap, a space, a region from which all the mercury had retreated and into which nothing had rushed to replace it, because the tube was sealed and there was nothing available to rush in. Torricelli had created a vacuum, a small, quiet, glass-enclosed pocket of nothing sitting above a column of heavy silver liquid in a laboratory in Florence. He understood immediately what had happened. The mercury was not being held up by some mysterious property of the tube or by any force from above. It was being pushed up by the weight of the entire atmosphere pressing down on the surface of the mercury in the open bowl. The column of mercury was simply the height at which the downward pull of gravity on the mercury exactly balanced the downward push of all that air above the ball. The vacuum at the top was not being maintained by anything. It was simply the space left behind when the mercury had nowhere further to fall. This was already a significant philosophical departure, but the truly dramatic demonstration came a few years later in the German city of Magdeburg, courtesy of a man named Otto von Guericke. Guericke was the mayor of Magdeburg, and he was also, in the way that certain remarkable people of his era managed to be, a serious natural philosopher with a passion for demonstration. He had built one of the first functional air pumps, a device capable of drawing air out of a sealed container and creating a partial vacuum inside. And in 1654, he used this pump to stage one of the most memorable public scientific demonstrations in history. He had constructed 2 hollow bronze hemispheres, each roughly 50 centimeters across, machined with enough precision that when they were placed together rim to rim, they formed a nearly perfect sphere. The join was sealed with a ring of leather soaked in oil and grease to make it airtight. Guericke then connected his pump to a valve in one of the hemispheres and drew out the air from inside, creating a partial vacuum within the sphere. The 2 halves were now held together by nothing but the pressure of the surrounding atmosphere pushing inward from all sides. He then invited 2 teams of horses, 8 horses on each side, 16 in total, to attempt to pull the hemispheres apart. They could not do it. Think about that image for a moment. 2 hollow bronze balls touching each other at a flat rim, held together by nothing visible, nothing mechanical, no bolt or clamp or glue, just the weight of the sky pressing in from outside and the absence of anything pushing back from within. 16 horses straining against that invisible grip could not separate them. When Guericke finally opened the valve and allowed air back inside, the 2 halves fell apart in his hands with no effort whatsoever. The Magdeburg hemispheres did something philosophically important beyond their theatrical spectacle. They made the vacuum tangible. They gave it presence. The vacuum inside those bronze bowls was not merely an absence. It was a condition that had measurable physical consequences. And yet, for the next 2.5 centuries, physicists largely continued to think of the vacuum as a passive thing. Yes, you could create one. Yes, it had properties you could measure, like the way it affected the pressure of surrounding gases. But the vacuum itself, the empty space at the heart of it, was understood to be inert. A container with nothing in it. A stage on which physical events could occur, but not itself a participant. By the late 19th century, this picture had become very confident. Classical physics, the magnificent framework built by Newton and Maxwell and their contemporaries, described a universe of matter and energy moving through space according to precise, deterministic laws. Space itself was the backdrop. It did not vibrate or fluctuate or do anything on its own. The vacuum was, in the classical view, the perfect void, silent, still, and absolutely at rest. It is worth pausing on how reasonable this seemed. If you cool a gas, the molecules slow down. Cool it further, the molecules slow further still. In principle, if you could reach the coldest possible temperature, what we now call absolute zero, approximately minus 273 degrees on the Celsius scale, all molecular motion would cease. Everything would stop, and the vacuum, which contains no molecules at all, would simply be the ultimate expression of that stillness. Perfectly cold, perfectly quiet, perfectly nothing. This was the picture at the dawn of the 20th century, and it was about to become very complicated. In the year 1900, a German physicist named Max Planck was wrestling with a problem that had been nagging at theorists for years. It concerned the way that objects emit light when they are heated, the way a metal rod glows dull red, then orange, then yellow-white as it gets hotter. Classical physics made a specific prediction about how the energy of this emitted light should be distributed across different wavelengths, and the prediction was catastrophically wrong. At short wavelengths, what we would call ultraviolet light and beyond, the classical prediction said the emitted energy should rise without limit, growing toward infinity. This was clearly nonsense, because hot objects do not emit infinite energy, and the prediction became known with a certain dry scientific humor as the ultraviolet catastrophe. Planck found a way to fix the prediction, but the fix required something radical. He had to assume that light, and more broadly energy itself, was not emitted continuously, the way water flows from a tap, but in discrete bundles, packets, chunks of a specific size that could not be subdivided. He called these packets quanta, from the Latin for how much. A single packet of light energy is what we now call a photon. Planck was not entirely comfortable with this idea. He initially hoped it was a mathematical trick rather than a description of physical reality. But it worked. The prediction matched the observations, and it planted a seed that would grow over the following decades into the complete overhaul of our picture of the universe. Then, in 1916, Albert Einstein was thinking about something related. He was working on the way atoms absorb and emit light, and he noticed something that classical physics could not easily explain. An atom in an excited state, one that has absorbed energy and is holding it, will eventually emit that energy as a photon and drop back to a lower energy state. Classical physics could explain this if there was some external disturbance, some nudge from outside to trigger the emission. But Einstein showed that atoms will sometimes emit a photon entirely on their own, without any apparent external cause. He called this spontaneous emission, and it troubled him, because it seemed to imply that something was triggering the emission even in an apparently empty environment. What was doing the triggering? The answer, which would take decades to fully develop, was the vacuum itself. Even in a region from which all matter and all radiation had been removed, there remained something, a residual activity, a background hum that was sufficient to nudge an excited atom into releasing its energy. The vacuum was not, it turned out, doing nothing at all. And this was only the beginning of what empty space was about to reveal. To understand why the vacuum is restless, you need to sit with one idea long enough for it to become genuinely strange. Not strange in a way that requires effort, but strange in the way that a familiar word becomes strange if you say it slowly enough, many times over. The idea is this: there are certain pairs of properties in nature that cannot both be precisely known at the same time, not because our instruments are inadequate, not because we haven't tried hard enough, but because the universe itself does not permit both quantities to be simultaneously exact. This is the Heisenberg uncertainty principle, named for the German physicist Werner Heisenberg, who articulated it in 1927. You may have encountered it in the form that involves position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. But there is another form of the same principle, and it is this second form that reaches down into the vacuum and makes it impossible for empty space to be truly still. The second form involves energy and time. Here is how to think about it. Imagine you are trying to measure the energy of a tiny region of space at a specific instant. To pin down the energy with great precision, you need to observe the region over a very long period of time. You need many, many measurements spread out to average toward an accurate value. But if you want to know the energy at a specific, precise instant, right now, at this exact moment, you have almost no time to gather information, and so your measurement of the energy becomes wildly uncertain. The two quantities, precision in energy and precision in the timing of that energy, you cannot have both. Now apply this to the vacuum. The classical picture says the vacuum has zero energy. perfectly, exactly zero. But for the vacuum to have precisely zero energy at a precisely defined moment, you would need nature to simultaneously specify both the energy and the time to perfect accuracy. And the universe will not allow this. The very act of demanding both quantities be exact is forbidden. What happens instead is that the energy of any tiny region of space must fluctuate. It cannot sit still at zero. It shudders, it trembles, it briefly rises above zero and then falls back and then rises again in a constant, inescapable restlessness. These fluctuations are not large. In most regions of space, they are vanishingly small. But they are real, and they are everywhere, and they never stop. To build intuition for this, think of a guitar string. When you pluck a guitar string and then place your finger on it to silence it, the vibration stops. Classical physics says that if you could cool the string to absolute zero temperature, the coldest temperature physically possible, where all thermal motion ceases, the string would be completely still, no vibration at all. But quantum mechanics says otherwise. Even at absolute zero, the string cannot be perfectly still, because for it to be perfectly still would mean that its displacement from rest and its momentum were both simultaneously zero, and that would violate the uncertainty principle. So even at absolute zero, the string retains a tiny, irreducible trembling, a whisper of motion that cannot be removed, no matter how cold you make the system. This irreducible motion is called zero-point energy. The energy that remains in a quantum system even at the lowest possible temperature, even in the lowest possible energy state. Every quantum system has it. A molecule has it. An atom has it. And the quantum fields that fill all of space have it too. This is where we need to introduce an idea that will carry us through the rest of tonight's journey. The idea that space is filled with fields. Not fields in the agricultural sense, but in the physics sense. A field is a quantity that has a value at every point in space. Temperature is a field. In a loose sense, every point in a room has a temperature. But quantum fields are something deeper and stranger than that. They are the fundamental fabric from which everything is made, and we'll explore them more fully in the chapter that follows. For now, what matters is this. Each of these fields, at every point in space, behaves a little like that guitar string at absolute zero. It cannot be perfectly still. It has zero-point energy. It fluctuates, not because anything is disturbing it from outside, but because the uncertainty principle will not permit it to be quiet. The vacuum, in this picture, is not the absence of these fields. The fields are always there, everywhere, filling all of space. The vacuum is simply the lowest possible energy state of all those fields taken together. And the lowest possible energy state of a quantum field is not zero energy. It is a state of constant, gentle, inescapable fluctuation. There is a way to feel the depth of this that goes beyond analogy. In classical physics, you can imagine turning a knob that controls the energy of a system, turning it all the way down to zero, reaching perfect stillness. In quantum mechanics, that knob has a physical stop, a point below which it cannot go, and at that stop, the system is still moving. You have reached the floor, and the floor is vibrating. The floor is vibrating. That is the vacuum. Now, you might ask, if the vacuum is fluctuating, what is it that's fluctuating? What is actually happening in that apparently empty space? The answer requires thinking about what particles really are, and it requires letting go of the image of a particle as a tiny sphere sitting in space. That image, comfortable as it is not what nature is actually doing. What quantum mechanics tells us, and what has been confirmed by a century of increasingly precise experiments, is that particles are not fundamental objects. They are disturbances. They are temporary shapes in something more fundamental. And that something more fundamental is the quantum field. Think again of the guitar string, not as a particle but as a medium. A wave can travel along the string, a ripple, a disturbance moving from one end to the other. The wave is not a separate object sitting on the string. It is a pattern in the string. It is the string doing something. When the wave passes, the string returns to its resting state and the wave is gone. It did not come from somewhere else. It was a temporary shape in something that was already there. Particles are like this. An electron is not a tiny ball sitting in the electron field. An electron is the electron field doing something, a localized ripple, a concentrated disturbance moving through the field the way a wave moves through water. When the electron is absorbed, when it interacts with something and disappears, the field returns to something closer to its resting state. The electron was always a pattern in the field, not a thing in space. And the vacuum fluctuations, the zero-point energy, the constant trembling that the uncertainty principle demands, are the field doing something even when there is no particle present. They are the quiet, unpatterned shuddering of the medium itself, not a wave traveling in any direction, not a particle moving through space. Just the field, restless at its lowest energy, unable to be still. This is why the vacuum cannot be empty. Not because we haven't found a way to empty it properly, not because some particle has sneaked in that we haven't detected, but because the fields that fill space are quantum fields, and quantum fields at every point, at every moment, are subject to the uncertainty principle, and the uncertainty principle will not permit them to be quiet. The restlessness of the vacuum is not an accident. It is not a flaw. It is woven into the deepest structure of what reality is allowed to be. Before quantum field theory, the framework that emerged in its modern form through the work of Shinichiro Tomonaga, Richard Feynman, and Julian Schwinger in the late 1940s and early 1950s, physicists thought of particles as the fundamental things. Electrons were small objects. They moved through space and interacted with each other according to precise rules, and space itself was the stage on which these interactions played out. Quantum field theory replaced this picture entirely, and the replacement is, once you let it settle, genuinely more beautiful than what it displaced. In the framework of quantum field theory, the fundamental things are not particles. The fundamental things are fields, and not one field, but many, a whole family of them, each associated with a different type of particle, each stretching without interruption across the entire universe, from one edge of the observable cosmos to the other. There is an electron field, there is a photon field, the field associated with light and with the electromagnetic force. There are quark fields, of which there are 6 distinct varieties. There is a field associated with the particles called muons, which are heavier cousins of the electron. There is the field associated with the Higgs particle, which gives mass to other particles through its interactions. And there are others. All of them present everywhere, all of them overlapping, all of them filling the same space simultaneously, the way different musical notes can fill the same room at the same time without interfering with each other. A particle, in this picture, is what the field looks like when it has been excited, when energy has been added to it in a localized region. The analogy of a wave on the ocean's surface is a good one, and it is worth dwelling on. The ocean is always there. It covers the surface, it has a certain resting state, a certain baseline. When wind passes over it, or when a stone is dropped into it, the surface is disturbed. A wave forms, a raised region, a concentrated pattern of energy moving across the surface. But the wave is not a separate object floating on top of the ocean. It is the ocean itself locally doing something different. An electron is the electron field locally doing something different. A photon is the photon field locally doing something different. When 2 electrons meet and interact and scatter apart, what is actually happening at the deepest level the theory describes is that the electron field and the photon field are exchanging energy in a localized region, and the result is that the 2 disturbances in the electron field move apart along new trajectories. Now here is where virtual particles enter the story, because they are central to understanding the vacuum, and they are often misunderstood. When two electrons approach each other, they repel. You know this, like charges push apart. But in the quantum field theory picture, this repulsion is not a mysterious action at a distance. It is mediated. Something passes between them. The photon field is briefly excited by the presence of the electrons, and this excitation, this temporary disturbance, is what we call a virtual photon. The word virtual here is doing important work. A virtual photon is not a photon in the full sense. It does not travel at the speed of light. It does not have the precise relationship between energy and momentum that a real photon has, and it cannot be detected directly as a particle. It exists only for the duration of the interaction, borrowing its existence from the uncertainty principle, which permits a brief fluctuation in energy provided it does not last too long. To be very precise about what is happening, the uncertainty principle says that the energy of a region of space and the duration of that energy state cannot both be exactly specified simultaneously. This means that for a very brief instant, the energy of a region can deviate from its average value. If the deviation is large, it lasts only a very short time. If the deviation is small, it can persist a little longer. Virtual particles are the names we give to these brief, localized deviations in the fields, disturbances that arise, exist momentarily, and then subside, returning the borrowed energy to the vacuum. The exchange of virtual photons between two electrons is not a rare or exotic event. It is happening continuously, everywhere that charged particles exist. Every time two electrons sit near each other, there is a constant, restless shuttling of virtual photons between them. This is not a description of what might be happening. This is the mechanism by which the electromagnetic force operates. The force you feel when you press your fingertips together and feel resistance. That resistance is, at the deepest level, the result of electrons in your fingertips exchanging virtual photons with electrons in the surface you are pressing against. The force that holds matter in its shape is made of the activity of the vacuum. Virtual particles are not limited to photons. Near a proton, the strong nuclear force, the force that holds the nucleus together, operates through the exchange of virtual particles called gluons, the excitations of the gluon field. And quarks, which are the constituents of protons and neutrons, are constantly surrounded by a cloud of virtual quarks and antiquarks, flickering in and out of existence, briefly separating from the vacuum and then recombining with it. The proton is not a neat little object containing exactly 3 quarks sitting quietly in a row. It is a dynamic, seething region of field activity, where the 3 real quarks are surrounded at all times by a churning sea of virtual quarks and gluons, all of them contributing to the proton's total energy and to its apparent mass. In fact, here is something remarkable. The mass of the 3 quarks that are considered the real constituents of a proton accounts for only about 1% of the proton's total mass. The remaining 99% comes from the energy of the virtual particles, the gluons and quark-antiquark pairs that fill the space inside. The matter around you, the atoms in your body, the chair or bed you are lying on. Almost all of its mass comes not from the mass of the fundamental particles, but from the energy of the vacuum activity within those particles. The vacuum is not contributing a little bit to the structure of matter. The vacuum is, in a very real sense, most of what matter is. There is something deeply quiet in this idea, once you let it arrive without rushing it. The solid world, the weight of a blanket, the firmness of a pillow, is mostly made of the restless humming of fields in their lowest energy state. The thing that feels most solid, most real, most present, is almost entirely composed of something that classical physics would have called nothing at all. The vacuum is not the absence of the world, it is the foundation of it. And the most direct proof of this the experiment that makes the vacuum's activity visible in a way you can almost hold in your hands, came in 1948 from a quiet prediction made by a Dutch physicist sitting at his desk in Eindhoven. Hendrik Casimir was 32 years old in 1948, and he was thinking about something that might easily have seemed like a technical footnote. He was working on problems in theoretical physics at the Philips Research Laboratories in the Netherlands, and he had been studying the forces between large molecules, the weak, distance-dependent attractions that exist between neutral objects, the kind of forces that allow geckos to walk on ceilings and that determine how liquids behave at surfaces. A colleague, Niels Bohr, mentioned in passing during a walk that Casimir's calculations seemed rather complicated. Casimir thought about this, and then he thought about the vacuum, and then he had an idea so elegant and so strange that it took a decade for anyone to be confident enough to test it. The idea was this: take two flat, perfectly conducting metal plates, the kind of plates that allow electrical charges to move freely across their surfaces. Place them facing each other, parallel, in a vacuum, with no electrical charge on either of them. Separate them by an extremely small gap, not the width of a hair, not the width of a bacterium, but the width of a few hundred atoms placed side by side, a gap of, say, 100 nanometers, which is 1/10,000th of a millimeter. Now, leave them there. Do nothing to them. Apply no force, no charge, no field. Just leave them facing each other in the dark. Casimir predicted that they would move toward each other, not because of any classical force, not because of gravity, which at this scale is negligible, not because of any electrical attraction, since both plates are neutral. They would move toward each other because of the quantum vacuum, because of the zero-point fluctuations of the photon field in the space around them. Here is the mechanism, step by careful step. The photon field, like all quantum fields, is fluctuating everywhere in space. These fluctuations can be thought of as virtual photons of many different wavelengths, some very short, some very long, all of them flickering in and out of existence at every point in space. In the open space far from the plates, all of these wavelengths are permitted. Short ones, long ones, every wavelength in between. The field fluctuates richly and freely. But between the plates, there is a constraint. The plates are conducting, which means that the electric field must be zero at their surfaces. This is a basic property of how conductors work. This constraint means that only certain wavelengths of virtual photons can exist in the gap between the plates. Specifically, only those wavelengths that fit neatly into the gap, where the gap width is exactly a whole number of half wavelengths, are permitted. If the gap is 100 nanometers, then the only standing patterns of the field that can exist in that gap are those whose half wavelength is 100 nanometers, or 50 nanometers, or 33 nanometers, and so on, the whole number divisors. All the other wavelengths are excluded. This means that inside the gap, there are fewer modes of vacuum fluctuation than outside. The field between the plates is, in a very specific sense, quieter than the field outside them. There is less zero-point energy between the plates than there is in the open space on either side. And this difference in energy density creates a pressure. The vacuum pushes on the plates from outside with its full complement of fluctuations. The vacuum pushes on the plates from inside with a reduced complement of fluctuations. The outside pushes harder than the inside. The plates are pressed together. This is the Casimir effect. Two neutral metal plates in a vacuum pressed together by the pressure of nothing, or rather by the pressure of what nothing actually is. The force is tiny. For plates 1 centimeter square separated by 100 nanometers, the predicted force is a few hundred piconewtons. A piconewton is 1/trillionth of a newton, and a newton is roughly the force required to hold a small apple in your hand against gravity. So we are talking about a force that is a trillionth of the weight of a small apple, acting across a gap smaller than the wavelength of visible light. This is not a force you could feel. It is a force you can barely imagine. and yet it was measured. The first attempt at experimental confirmation came in 1958, 10 years after Casimir's prediction, by a Dutch physicist named M.J. Sparnay. Sparnay's experiment was extraordinarily difficult. The plates had to be made flat enough that their surfaces did not diverge by more than a tiny fraction of the gap width. Any tilt would change the effective separation and ruin the measurement. They had to be kept free of electrical charge, because even a tiny residual charge would create an electrical force far larger than the Casimir force and swamp the signal. They had to be placed in a genuine vacuum, since even a thin layer of air would change the properties of the gap. And the force itself had to be measured with extraordinary delicacy. Sparnay's results were encouraging but not conclusive. His measurements were consistent with Casimir's prediction, but his experimental uncertainties were large enough that he could not rule out other explanations. He reported, with admirable scientific honesty, that his results did not contradict the Casimir effect. The definitive confirmation had to wait until 1997, when a physicist named Steve Lamoureux, working at the University of Washington, performed a measurement of the Casimir force with a precision that left almost no room for doubt. Lamoureux's apparatus was a work of exceptional ingenuity. Rather than two flat plates, which are extraordinarily difficult to keep perfectly parallel at nanometer separations, he used a flat plate and a sphere. A sphere, touching a flat surface, makes contact at a single point, and the geometry of a sphere and plate system is much easier to calculate and control than two parallel plates. He suspended his flat plate from a torsion pendulum, a device that measures tiny forces by how much they twist a delicate fiber, and brought the sphere toward it while carefully monitoring the twist. He measured the Casimir force as a function of the separation between sphere and plate, ranging from about 600 nanometers down to about 100 nanometers. His measured values matched Casimir's theoretical prediction to within 5%. 5% for a force that is a trillionth of the weight of a small apple, for a force produced by the quantum vacuum, by the zero-point energy of the photon field in the gap between two pieces of metal. The Casimir effect is now one of the most precisely confirmed predictions in experimental physics. Subsequent measurements have refined the agreement further, and the effect has been measured in different geometries at different separations with different materials. It is real, it is reproducible, and its existence tells us, beyond any reasonable doubt, that the quantum vacuum is not any reasonable doubt. It is active, it has energy, and that energy has measurable physical consequences that you can, with sufficient care and sufficiently delicate instruments, reach out and touch. There is something to sit with in that image. The space between two metal plates, the gap that contains, by every classical measure, nothing at all, is in fact a region where the vacuum is constrained, where some of its fluctuations are excluded, and where this exclusion produces a real, measurable force. The silence is singing just below the range of any ordinary hearing. And the effects of the vacuum do not stop at forces between plates. They reach inside the atom itself. In the years immediately following the Second World War, the physics of the atom was in a peculiar state. The quantum theory of the hydrogen atom, the simplest atom, a single proton with a single electron orbiting it, was extraordinarily successful. It predicted the energies of the electrons' allowed orbits with remarkable accuracy, and those predictions had been confirmed by spectroscopy, by shining light at hydrogen atoms and measuring precisely which colors they absorbed and emitted. The theory worked. But a nagging question remained. The theory, specifically the version developed by Paul Dirac in 1928, which unified quantum mechanics with Einstein's special theory of relativity, predicted that two particular energy levels of the hydrogen atom should be exactly identical. These two levels are both associated with the electron in the second shell of the atom, the first shell above the innermost one, but they differ in a subtle way related to the electron's angular momentum, the way it is oriented as it moves around the nucleus. Dirac's theory said the energies of these two states should be precisely the same. Degenerate in the technical sense, meaning they occupy the same energy like two different paths that arrive at the same height. In 1947, Willis Lamb and his research assistant Robert Rutherford decided to check this. They used a technique involving microwave radiation, radio waves of a very specific, precisely tunable frequency, to probe the energy difference between these two levels. If Dirac was right, there would be no difference, and the microwave radiation would have no effect. If there was a difference, they would be able to measure it. There was a difference. A small one, but a real one, and one that could be measured with precision. The two energy levels that Dirac's theory said should be identical were, in fact, separated by a tiny gap, an energy difference corresponding to a frequency of about 1058 megacycles per second, which is in the microwave range of the spectrum. This shift in energy, the shift away from where the theory predicted, became known as the Lamb shift. The discovery earned Lamb the Nobel Prize in Physics in 1955. But the more interesting question, for our purposes tonight, is not the fact of the discovery, but its explanation. Why are those two energy levels different? What is pushing them apart? The answer is the vacuum. The electron orbiting the hydrogen nucleus is not moving through empty space. It is moving through the quantum vacuum, through the sea of fluctuating fields that fills all of space, including the space inside the atom. The photon field, in particular, is fluctuating everywhere, including in the region where the electron spends its time. And these fluctuations, these constant, inescapable tremors in the electromagnetic field, are continually nudging the electron, jostling it slightly off the trajectory it would otherwise follow. The jostling is tiny. The electron is not being thrown around dramatically. It is being very gently perturbed, the way a leaf floating on very still water is very gently disturbed by the surface tension, fluctuations of the water itself. But even a tiny perturbation, when it acts constantly and in a slightly different way on electrons in different orbital states, is enough to shift the energy levels apart. The reason the two states are affected differently is related to the shape of their wave functions, a term we should explain. In quantum mechanics, a wave function is the mathematical description of where a particle is likely to be found. It is not a trajectory, like the orbit of a planet. It is a probability distribution, a cloud of likelihood spread through space. For the two states in question, the electron's probability cloud has different shapes. One of the states has a probability cloud that spends more time near the nucleus, literally closer, on average, to the proton at the center. The other state has a cloud that is more spread out, spending more time at larger distances. The vacuum fluctuations of the photon field affect the electron more strongly when the electron is closer to the nucleus, because the electric field of the nucleus is stronger there, and the interaction between the electron's charge and the vacuum fluctuations is amplified by the strength of the local field, so the two states are nudged by different amounts. The state that spends more time near the nucleus gets nudged more. Its energy shifts by a larger amount, and the two states, which Dirac's theory placed at the same energy, are pulled apart. The shift is small. It corresponds to a photon of microwave radiation, far less energetic than visible light. But it is precisely calculable because the theory of quantum electrodynamics, the quantum field theory of the electromagnetic force, developed in the years immediately following Lamb and Rutherford's measurement, provides a systematic way to calculate the effects of vacuum fluctuations on any quantum system. When the calculation was performed by Hans Bethe, initially in a remarkable back-of-the-envelope calculation on a train journey shortly after the 1947 measurement was announced, and then more rigorously by Feynman, Schwinger, and Tominaga, the result matched the measured value with extraordinary precision. How extraordinary! The Lamb shift has now been measured and calculated to an agreement of better than 1 part in 10 billion, 10 decimal places. This is not a rough match. It is not an approximate confirmation. It is one of the most precisely verified predictions in the entire history of science, comparable only to the magnetic moment of the electron, another quantity whose calculation requires accounting for the effects of the vacuum. What this precision means is worth dwelling on. The calculation of the Lamb shift requires adding up the contributions of virtual photons of every possible wavelength, every possible energy, flickering in and out of the vacuum around the hydrogen atom. Each virtual photon contributes a tiny amount to the shift. The sum of all those contributions across an effectively infinite range of photon energies gives a finite, specific, calculable number. And that number, when compared to what Lamb and Rutherford measured with their microwave apparatus in 1947, matches. The vacuum is not a theoretical convenience. It is not a mathematical placeholder. It is a physical reality that leaves a specific, measurable fingerprint on the structure of the hydrogen atom, the simplest atom in the universe. And that fingerprint has been read with a precision of 10 decimal places. The virtual photons that nudge the electron in hydrogen are the same virtual photons that mediate the electromagnetic force between charged particles, the same quantum vacuum fluctuations that the Casimir effect makes tangible between two metal plates. They are all expressions of the same underlying truth that the quantum fields filling space are never quiet, that their restlessness is not peripheral but fundamental, and that the atom sitting at the heart of every molecule in your body has a slightly different energy than it would have if the vacuum were truly empty. You are shaped, in the most literal sense, by the activity of nothing. The event horizon of a black hole is one of the strangest boundaries in nature. It is not a surface you could touch. There is no wall there, no membrane, nothing solid. It is simply the point of no return, the distance from the black hole's center at which the gravitational pull becomes so strong that not even light, moving at the fastest speed anything can move, can escape. Inside the horizon, everything, light, matter, information, falls inward. Outside it, things can, in principle, still get away. For most of the history of black hole physics, the event horizon was thought to be a passive boundary. Things fell in, nothing came out. A black hole was, in the classical picture, a one-way door in the fabric of space-time, and the door only opened inward. In 1974, Stephen Hawking showed that this picture was incomplete. Not wrong exactly. In classical physics, it is correct. But when you take into account the quantum vacuum, something remarkable happens at the horizon. Hawking's argument begins with the virtual particle pairs that the vacuum is constantly producing everywhere in space. We have already met these pairs. The uncertainty principle permits a temporary fluctuation in the energy of any region of space, and this fluctuation can manifest as a particle and its corresponding antiparticle flickering into existence together. Under normal circumstances, far from any black hole, the pair exists for a brief moment and then recombines, the particle and antiparticle annihilating each other and returning their borrowed energy to the vacuum. The whole process is invisible. The pair appears, exists for an instant, and vanishes, leaving no lasting trace. But right at the edge of a black hole's event horizon, the situation is different. The horizon is not a gradual boundary, it is a precise threshold. On one side of it, escape is possible. On the other side, it is not. And when a virtual particle-antiparticle pair forms in the extreme vicinity of this boundary, it is possible, not guaranteed, but possible, for the pair to straddle the horizon at the moment of its formation. One member of the pair finds itself just outside the horizon. When this happens, the two particles cannot recombine. The one inside the horizon is already falling inward, pulled by gravity toward the singularity at the black hole's center. It cannot reach back across the horizon to meet its partner. The two members of the pair, which under normal circumstances would annihilate each other almost immediately, are permanently separated by the one boundary in nature that cannot be crossed in both directions. The particle outside the horizon is now in an unusual situation. It has no partner to annihilate with. It cannot simply disappear back into the vacuum because the vacuum fluctuation that produced it has been interrupted, and so it does the only thing it can do. It becomes real. It flies outward into space as a genuine, detectable particle, carrying real energy away from the vicinity of the black hole. This escaping radiation is what Hawking predicted, and it has been called Hawking radiation ever since. But where does the energy come from? Energy is conserved. It cannot simply be created. If a real particle is flying away from the black hole carrying energy, that energy must come from somewhere. And the answer, in Hawking's analysis, is that it comes from the black hole itself. The infalling partner, the particle that fell inside the horizon, carries negative energy in this context, in a technically precise sense related to how energy is defined in the curved space-time near a black hole. When the black hole absorbs this negative energy particle, its total energy decreases, its mass decreases. The black hole, over the course of an enormous number of such events, very slowly loses mass. The black hole is evaporating. The rate at which it evaporates depends on its mass. A more massive black hole evaporates more slowly. The temperature of the Hawking radiation, the energy of the particles being emitted, is inversely proportional to the black hole's mass. A black hole with the mass of our Sun would emit Hawking radiation at a temperature of about 60 nanokelvins, which is 60 billionths of a degree above absolute zero. This is vastly colder than the cosmic microwave background radiation that fills the universe, the faint afterglow of the early universe, which has a temperature of about 2.7 degrees above absolute zero. Since the background radiation is hotter than the Hawking radiation, a solar mass black hole actually absorbs more radiation from its environment than it emits, and it grows rather than shrinks. For a black hole to evaporate, it would need to be small enough that its Hawking temperature exceeded the temperature of the cosmic background, which means smaller than roughly 100 trillion kilograms, far less massive than any black hole we have observed in nature. But the principle holds. Given enough time, any black hole, if left in isolation in a universe cold enough, will eventually evaporate completely. How long is enough time? The time scale for a solar mass black hole to evaporate completely, starting from the moment the universe becomes cold enough for evaporation to dominate over absorption, is almost beyond description. It is approximately 10 to the power of 67 years. Written out, that is a 1 followed by 67 years. The current age of the universe is about 14 billion years, which is approximately 1 followed by 10 zeros. The evaporation timescale is not just long compared to the age of the universe. It is incomprehensibly, almost insultingly longer. The universe would need to be not twice as old, not a million times as old, but a billion times as old as it is now before a solar mass black hole had finished evaporating. And yet, Hawking's analysis says it would happen, particle by particle, fluctuation by fluctuation. The vacuum would slowly, patiently, inexorably drain the black hole of its mass until there was nothing left. This raises a question that has occupied physicists for 50 years and has not yet been fully resolved. When the black hole evaporates, what happens to the information about everything that ever fell in? Information, in the physics sense, means the precise quantum state of every particle, its position, its momentum, its spin, its every property. In ordinary quantum mechanics, information is never destroyed. The laws of quantum mechanics are reversible. Given the final state of a system, you can, in principle, reconstruct its initial state. But if a black hole swallows information, swallows a book, a star, a person, and then evaporates into Hawking radiation, is the information in the Hawking radiation? Is it scrambled but recoverable, or is it simply gone? This is called the black hole information paradox, and it sits at the intersection of quantum mechanics and general relativity, the two great frameworks of modern physics that have never been fully reconciled with each other. Hawking himself initially believed the information was lost, then later came to think it might be preserved. What is not in question is the physics that generates the radiation in the first place. The quantum vacuum, fluctuating at the edge of the event horizon, is doing something. It is not passive. It is not merely a backdrop. At the most extreme boundary that nature provides, the point of no return around a black hole, the restless activity of the vacuum becomes something that even gravity cannot ignore. The vacuum flickers even at the edge of the abyss. There is a number that sits at the heart of modern physics, like a splinter that cannot be removed. It is not a difficult number to state. It is simply the ratio between two quantities, the energy density of the quantum vacuum as theorists calculate it, and the energy density of the vacuum as astronomers measure it. The ratio is approximately 10 to the power of 120. Written out, the calculated value is larger than the measured value by a factor of 1, followed by 120 zeros. This is not a small discrepancy. It is not a rounding error. It is the largest known disagreement between a theoretical prediction and an experimental observation in the history of physics. It has been called, without much exaggeration, the worst prediction in science. To understand why this discrepancy exists and why it is so difficult to resolve, we need to understand both numbers separately. The measured number comes from cosmology, from observations of the large-scale structure and behavior of the universe. In 1998, two independent teams of astronomers studying very distant supernovae, exploding stars used as cosmic distance markers, discovered something unexpected. The expansion of the universe, which everyone had assumed was slowing down under the mutual gravitational attraction of all the matter within it, was in fact speeding up. The universe is not decelerating, it is accelerating. Something is pushing the fabric of space apart, and the push is getting stronger as the universe grows larger. This something was quickly identified with a concept that Einstein had introduced in 1917 and then abandoned, the cosmological constant. Einstein had originally added it to his equations of general relativity, the equations that describe how matter and energy curve, space-time, and how that curvature drives the motion of matter, as a term representing the energy of empty space itself. He had added it to make a static universe possible, and when Edwin Hubble's observations in the late 1920s showed that the universe was expanding, Einstein removed the term and reportedly called it his greatest blunder. But the 1998 supernova observations brought it back. The cosmological constant, now understood as the energy density of the vacuum, the energy that empty space carries simply by virtue of existing, is real, and it is driving the accelerated expansion of the universe. Its measured value is very small, approximately 7 times 10 to the power of negative 27 kilograms per cubic meter in energy density terms. A tiny but non-zero energy pervading all of space, gently and persistently pushing everything apart. Now for the theoretical number. In quantum field theory, you can calculate the energy density of the vacuum by summing up the zero-point energy of every possible mode of every quantum field. Every field, at every point in space, at every possible frequency of fluctuation, contributes its half quantum of energy to the vacuum. The sum over all frequencies for any given field rises without limit. In principle, it is infinite. But physicists have a standard procedure for dealing with this. They impose a cutoff, a maximum frequency above which they trust the theory to be valid. The most physically natural cutoff is the Planck scale, the energy scale at which quantum effects and gravitational effects become comparable in magnitude, and beyond which our current theories are almost certainly incomplete. When you calculate the zero-point energy of the vacuum up to this cutoff and compare it to the measured cosmological constant, you get the factor of 10 to the power of 120. The theoretical vacuum energy is 10 to the 120th power times larger than the observed vacuum energy. Not 10 times, not 1,000,000 times, 10 to the power of 120 times. This is the cosmological constant problem, and it is one of the deepest unsolved problems in all of physics. There are several ways physicists have tried to approach it. One possibility is that the bare vacuum energy, the contribution from the quantum fields, is indeed enormous, but that it is almost exactly cancelled by some other contribution, leaving only the tiny residual that we observe. This would require a cancellation of extraordinary precision. The two contributions would need to cancel each other to 120 decimal places, with only the tiniest remainder surviving. This kind of fine-tuning is not impossible, but it is deeply unsatisfying, because it requires the universe to have been arranged with a precision that seems to demand explanation. Another possibility is that the cutoff should not be set at the Planck scale, that our theoretical framework breaks down earlier and the true cutoff gives a much smaller vacuum energy. But it is not clear where a more natural cutoff would be, and different choices give different answers. A third possibility is that the cosmological constant is not actually the vacuum energy at all, that the two are separate things, and we have been wrong to identify them. But this does not resolve the problem, it merely relocates it. And a fourth possibility, explored by some theorists, is that there is a symmetry in nature, a hypothetical symmetry called supersymmetry, in which every particle has a particle of opposite statistical character. That would cause the bosonic contributions to the vacuum energy to precisely cancel the fermionic contributions, leaving a vacuum energy of exactly zero. But we know the observed vacuum energy is not zero. It is small, but non-zero, and we have not found any experimental evidence for supersymmetry at the energies we can currently probe. So if supersymmetry exists, it is a broken symmetry, and the cancellation is imperfect, and we are back to explaining why the imperfection is so precisely tiny. The problem has no accepted solution. It is open. But even as the theoretical picture remains unresolved, experimental physics has been opening new windows into the vacuum. In February 2026, a large collaboration of physicists called the STAR Collaboration, working at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory in New York, published results that offered a remarkable new view of the vacuum's role in shaping ordinary matter. The experiment involved accelerating protons to very nearly the speed of light, to about 99.996% of it, and colliding them. In these collisions, the energy is so concentrated, the conditions so extreme, that the vacuum itself is briefly and violently disturbed. Particles emerge from the collision in large numbers, and among them are particles called lambda and anti-lambda baryons, heavy particles, each containing 3 quarks, but different combinations of quarks from the protons and neutrons we are familiar with. What the STAR collaboration found was that when a lambda and an anti-lambda emerged close together from one of these collisions, their spins were correlated. Spin is a quantum property of particles, an intrinsic angular momentum, a kind of internal rotation, and when two particles have correlated spins, it means that measuring the spin of one gives you information about the spin of the other, no matter how far apart they subsequently travel. This kind of correlation is called entanglement, and it is a signature of particles that share a common quantum origin. The lambda and anti-lambda particles each contain a strange quark and a strange antiquark respectively among their 3 quark constituents. The star collaborations analysis suggested that these strange quarks and antiquarks had originated as entangled pairs from the quantum vacuum, virtual quark, antiquark pairs that had been promoted to real particles by the energy of the collision, retaining the spin correlation they had as virtual partners in the vacuum. The spin alignment they measured was consistent with the particles having emerged from the same vacuum fluctuation, carrying the quantum entanglement of their virtual origin into the real world. This is a remarkable thing. It suggests that the properties of real, observable matter, in this case the spin of particles emerging from a high-energy collision, carry the imprint of the quantum vacuum from which they came. The vacuum does not merely influence matter from outside, nudging it gently the way virtual photons nudge the electron in hydrogen. It seeds matter from within, contributing the very quantum correlations that define the particle's properties. The vacuum is not a background condition. It is a participant. It is woven into the identity of every particle that has ever existed. And yet we cannot calculate its total energy to within a factor of 10 to the 120. We can measure its effects to 10 decimal places in the Lamb shift, and we cannot predict its overall magnitude to within 100 orders of magnitude in cosmology. Both of these things are true at the same time, and the tension between them is one of the most honest reflections of how much remains to be understood about the nature of space itself. We have come a long way tonight, from Aristotle's conviction that nothing was impossible, through Torricelli's mercury tube and Guerrica's bronze hemispheres and Casimir's quietly revolutionary prediction, through the uncertainty principle and the quantum fields that fill all of space, through virtual particles and the Lamb shift and Hawking radiation and the deepest unsolved problem in physics. And now, in the last hour of the night, we arrive somewhere quieter. Not at a conclusion exactly, more at a resting place, a place where the science can breathe and where you can breathe alongside it. Because there is something in all of this that reaches beyond the laboratory, beyond the equations and the experimental apparatus and the careful measurement of forces measured in trillionths of newtons. There is something in the picture of the quantum vacuum that feels, if you let it, genuinely comforting, genuinely restful. And I want to try to say what that is. The vacuum, as we have explored it tonight, is the lowest energy state of all the quantum fields that fill space. It is as quiet as those fields can possibly be. It is the universe at rest, and yet it is not still. It cannot be still. The uncertainty principle, that deep, irrevocable feature of the way reality is structured, will not permit it. Even at the floor of all possible energy, even in the state that is as close to nothing as anything can be, there is a residual hum, a 0-point trembling, a constant, patient, irreducible activity that no amount of cooling, no amount of isolation, no amount of emptying can remove. The universe, at its most rested, is still doing something. And here is what I find quietly remarkable about that. Lying here in the dark, right now, as you settle into sleep, your brain is doing something very similar. In the deepest stages of sleep, the stages that researchers call slow wave sleep, or deep NREM sleep, the stages that your brain moves into in the first few hours after you close your eyes, the electrical activity of the cortex shifts into a pattern of slow rolling waves. These are delta waves, oscillating between about half a cycle per second and 4 cycles per second. They are the slowest electrical rhythms the brain produces, and they are associated with the most profoundly restorative phase of sleep. During deep, slow-wave sleep, the conscious mind is absent, There is no experience of self, no narrative, no awareness. And yet the brain is far from inactive. Memories are being consolidated. The traces of the day's experiences are being quietly sorted, strengthened, and filed away in long-term storage. The glymphatic system, a network of channels that runs alongside the brain's blood vessels and acts as a kind of drainage system, becomes dramatically more active, flushing out metabolic waste products that accumulate during waking hours. Growth hormone is released in its largest pulse of the day. Synaptic connections are pruned and refined, the neural architecture of the brain quietly reorganized for the day ahead. None of this is experienced. None of it is visible from outside. The sleeping person appears still, their breathing slow, their face relaxed, their eyes motionless beneath closed lids. And yet the brain, far from resting in the sense of doing nothing, is doing some of its most important work. There is a resonance here with the quantum vacuum that is not merely poetic. Both the sleeping brain and the vacuum are in their lowest energy state, as quiet as they can be. And in both cases, that lowest energy state is not stillness. It is a particular kind of activity. Slow, deep, unhurried, purposeful in a way that does not announce itself. The delta waves of deep sleep wash through the cortex at roughly 1 to 2 cycles per second. Each wave represents a coordinated shift in the electrical state of millions of neurons. A slow tide of activity moving across the surface of the brain, and then receding, and then returning. The rhythm is ancient. It predates human consciousness. It is present in the deep sleep of every mammal that has been studied, from mice to elephants to whales. It is one of the most conserved features of the vertebrate nervous system, something that evolution has maintained across hundreds of millions of years, because whatever it is doing, it is important enough to be worth the cost. The zero-point energy of the vacuum has been present since the first moments of the universe. The delta rhythm of deep sleep has been present since long before there were minds to know that they were sleeping. Both are irreducible. Both are ancient. Both are doing something that the apparent silence of their surface does not reveal. And you are participating in both right now. The atoms that make up your body, the carbon, the hydrogen, the oxygen, the nitrogen, the iron, are all saturated with the quantum vacuum. The electrons in those atoms are being gently jostled by virtual photons, their energy levels shifted by fractions too small to measure without extraordinary instruments. The nucleons in the nuclei of those atoms are surrounded by clouds of virtual quarks and gluons, their mass drawn mostly from the restless activity of the vacuum inside them. The space between your atoms, the vast majority of the volume of what you think of as your body, is filled with quantum fields at their lowest energy state, trembling with zero-point energy that cannot be removed. You are held within the hum. You are part of it. You have always been part of it. And as your brain moves deeper into sleep tonight, as the fast, anxious rhythms of the waking day, the beta waves of attention and worry and planning, slow and give way to the long, rolling delta waves of deep restoration, something analogous is happening. The conscious processing, the narrative, the self-awareness, these are the excited states, the ripples on the surface of the field. Sleep is the field returning toward its resting state, not to nothing, never to nothing, but to something quieter and deeper and more fundamental than the waking mind can access. The vacuum does not know it is the vacuum. It does not experience its own restlessness. The virtual particles that flicker in and out of the photon field do not know they are virtual. The zero-point energy of the electron field does not know it is irreducible. These things simply are. They happen continuously, without witness, without effort, without any need for acknowledgement. Sleep is a little like this. The deepest sleep asks nothing of you. It does not require your attention or your effort or your awareness. It happens to you and in you and because of you without any conscious participation on your part. The restoration that is happening right now, the quiet, patient work of consolidation and repair and renewal, does not need you to supervise it. It is as automatic and as ancient and as reliable as the zero-point energy of the vacuum. There is something in this that might be worth carrying with you if you carry anything at all from tonight. The universe is not empty at its quietest. You are not empty at your quietest. The stillness that feels like absence is not absence. It is presence of a different kind, slower, deeper, more patient than the kinds of presence we can easily notice. The space between your thoughts is not nothing. The silence between heartbeats is not nothing. The darkness behind your closed eyes is not nothing. All of it is filled with something patient and ancient and continuous, something that has been there since before there were thoughts to have or eyes to close, something that will be there long after every star has cooled and every black hole has finished its slow evaporation. The vacuum does not rest. It cannot rest. And in its inability to rest, in its inescapable, gentle, perpetual hum, there is a kind of companionship, a reminder that the universe is not indifferent to its own existence, that even at its lowest, most rested, most apparently empty state, something is still happening. You are not alone in the dark. The dark itself is alive with something. The sentences can grow shorter now. The pace can slow. There is nothing more that needs to be said tonight, and the night itself is patient. Whatever you are carrying, you can set it down. The vacuum will still be there when you wake. The fields will still be trembling. The zero-point energy will still be present in every atom of everything in every corner of the universe, doing its quiet, irreducible work. And you will have slept. And the day will come when it comes. And somewhere beneath it all, something ancient and unhurried will still be humming. And so we leave it there. Somewhere behind you, the day is already distant. Let it stay where it is. Drift now, if you're ready. Sleep well.